We have sent spacecraft to every single planet in this solar system. Rovers are driving across Mars right now as you watch this. A probe was dropped through the clouds of Saturn. We photographed Pluto from less than 8,000 miles away. A rock so far out that the sun looks like just another star from its surface. Crossing billions of miles of empty space has started to feel almost normal, almost routine. But there is one direction we have barely touched. One place that should be the easiest to reach and turns out to be one of the hardest places in the entire solar system to get to. It is not some distant moon. It is not the edge of the galaxy. It is straight up, directly above the sun or directly below it, the vertical exit from our solar system. And we have almost never gone there. It sounds almost insulting in its simplicity. Just point the rocket up and go. How hard can it be? The answer is so counterintuitive that even people who work in space exploration find it genuinely uncomfortable to think about. What follows is the full story. Why going straight up is harder than reaching Pluto. What is actually waiting up there if we ever make the trip. And the insane maneuver scientists are now seriously considering, where a spacecraft has to first fall toward the sun before it can ever climb away from it. Here is something nobody tells you. Right now, without doing anything, you are moving, not slowly. The Earth is traveling around the sun at roughly 30 kilometers per second. That is about 67,000 miles per hour. Every single second, the ground beneath your feet is moving 30 kilometers sideways through space. Every rocket we have ever launched from this planet inherited that motion the moment it left the ground. This is normally a gift. When we want to go to Mars, that existing sideways speed does most of the work. A few extra kilometers per second in the right direction, and the spacecraft is on its way. The solar system is built flat, like a disk, and everything in that disk is already moving in the same general direction. Going sideways is easy. We have gotten very good at going sideways, but the moment you want to go straight up, not toward Mars, not toward Jupiter, not anywhere in the flat disk, straight up, perpendicular to everything, that sideways motion becomes your enemy. To escape vertically, you first have to cancel out those 30 kilometers per second you are already carrying. Cancel them completely. Then you have to build entirely new velocity in the upward direction. The total energy required is not slightly more than a normal mission. It is not twice as hard. It is almost 10 times harder. Mission planners measure this in something called delta V, the change in velocity a spacecraft has to produce on its own. Getting to Mars from Earth orbit needs about 4 kilometers per second of delta V. Going straight up out of the plane needs roughly 30 kilometers per second. That is not a bigger rocket problem. That is a fundamentally different category of difficulty. This is what makes it a prison. Earth's orbital motion gives us free speed in one direction and walls us in everywhere else. We can hop between planets in the same disk with relatively modest effort. But the moment we try to leave the disk itself, we are fighting 4.6 billion years of accumulated orbital momentum all at once. And here's the fact that should genuinely stop you for a moment. Reaching Pluto, 3.5 billion miles away, requires less energy than reaching a point just a few million miles directly above the sun's north pole. Distance is almost irrelevant. Direction is everything. Because escaping vertically is so expensive, almost no spacecraft has ever gone there, which means that in 2026, the regions directly above and below our own sun are still almost completely unexplored. We have detailed maps of Mars, high-resolution images of Pluto, close-up photographs of comets, asteroids, the rings of Saturn, and the moons of Jupiter. But the poles of the nearest star to Earth have barely been seen, not because we are not curious, because getting there is nearly impossible. This matters more than it sounds. The polar regions of the sun are where the most violent and most important solar activity happens. The fastest solar winds come from up there. The magnetic field of the entire sun reverses itself every 11 years through processes that start at the poles. The space weather that affects satellites, power grids, and communications across the entire solar system is shaped by what happens above and below the sun's equator. And we have been observing all of it almost entirely from the side. It is like trying to understand the entire weather system of a planet by only ever standing at the equator and looking straight ahead. Only 2 missions have ever managed a real polar view of the sun. The first was Ulysses, launched in 1990. To get out of the flat disk, Ulysses had to take an enormous detour. It first flew all the way out to Jupiter and used the gas giant's gravity like a slingshot to bend its trajectory nearly 80 degrees out of the plane. It worked. Ulysses gave us our first real measurements of the fast solar wind streaming from the poles, but it was built with 1980s instruments. No cameras capable of actually imaging the poles. We learned conditions. We never actually saw anything. The second mission is happening right now. Solar Orbiter, launched by the European Space Agency in 2020, has been slowly tilting its orbit using gravity assists from Venus. In March 2025, it sent back the first direct images of the sun's south pole ever taken in human history. The pictures show a chaotic, magnetically tangled region, nothing like the smoother solar surface visible from Earth. Think about what that means. Until last year, no human or machine had ever seen what the top or bottom of our own sun actually looks like, the closest, brightest, most important object in our local universe. And 2 entire regions of it had never been photographed. There is a second reason the vertical escape matters, and this one is genuinely unsettling once it lands. We do not actually know what our own solar system looks like from the outside. The sun produces a constant stream of charged particles called the solar wind. This wind flows outward in every direction and inflates a vast bubble around the sun called the heliosphere. Everything we have ever known lives inside this bubble. Every planet, every moon, every comet, every spacecraft ever launched, every human who has ever existed. The heliosphere is our home in the galaxy, and outside it lies the deep interstellar environment filled with cosmic rays and particles our bubble shields us from. For decades, scientists assumed the heliosphere was shaped like a comet, a rounded front pushing against the interstellar wind, and a long tail streaming out behind. This is the mission architecture that astrodynamicists now believe could finally give us a clean view of what lies directly above and below our star. It has never been done. The engineering required is at the edge of what is currently possible, but it is no longer science fiction if a spacecraft ever pulls this off. What does it actually find? The first thing that changes is the view itself. The plane of the solar system is dirty. Every planet, including Earth, moves through a thin haze of dust, debris left over from billions of years of comet passes, asteroid collisions, and the slow grinding of the solar system against itself. You can actually see this dust with your own eyes on a very dark, clear night just after sunset or before dawn. A faint pyramid of light rising from the horizon called the zodiacal light. That glow is sunlight bouncing off the dust cloud you are swimming through right now. A spacecraft climbing above the ecliptic would rise out of this dust layer within months. The view from above is dramatically cleaner, less scattered light, less background noise. The kind of environment where a telescope could detect extremely faint signals that, from inside the disk, are completely drowned out by the surrounding haze. Scientists have noted that a position above the ecliptic would be one of the best possible locations in the solar system for searching for signs of life around other stars. The noise floor drops, the signal gets clearer, the solar environment itself changes too. Above the sun's equatorial region, the slow solar wind, turbulent plasma moving at around 400 kilometers per second, gives way to something fundamentally different. Above the polar coronal holes, there is a fast solar wind stream moving between 700 and 800 kilometers per second. Thinner, smoother, more consistent. A spacecraft riding through this stream would be operating in a radiation environment unlike anything any mission has ever experienced, with real consequences for both its instruments and what it can measure. And then there is the biggest picture of all. From a vantage well above the disk, the solar system becomes visible as the flat ring it actually is. The planets in their orbits around the sun, the dust hugging the plane, the heliosphere wrapped around all of it in whatever shape it truly has. The entire structure of our home in the galaxy, visible as a single image. For the first time, we have photographed galaxies billions of light years away. We have imaged black holes. We have mapped the surface of Mars in higher resolution than many places on Earth. But the one photograph that has never existed, looking down at our own solar system from outside its plane, is still missing. No human, no robot, no probe has ever sent it back. That image is out there waiting, and the only thing standing between us and it is one of the hardest problems in astrodynamics, and the willingness to first fall toward the sun before we can ever climb away from it.